Today we want to talk about a few more details about diagonalization. Let's remind ourselves. A is an n by n matrix, so this is a thing that we apply to square matrices. A is diagonalizable if there's a diagonal matrix D and an invertible matrix P such that A is equal to PDP inverse. So what we found out is that the diagonal matrix D is going to be a matrix of eigenvalues. And the invertible matrix P is going to be a matrix of the eigenvectors. Since A is equal to P times D times P inverse, and P needs to be invertible, and A is n by n, that means D is also going to have to be n by n. So since P is supposed to be invertible, P is going to have to be square. And just the sizes of everything force D to be a square matrix as well. So we know how to build this. We find the eigenvalues of the matrix, we find the corresponding eigenvectors, and then we can possibly diagonalize the matrix. So one of the things that's a result of that results from this is that since we need to be able to make this invertible matrix where the columns are eigenvectors, A needs to have n linearly independent eigenvectors. So we can conclude from this that A is diagonalizable if A has n linearly independent eigenvectors. We need the linearly independent eigenvectors to make the matrix. So we can make an invertible matrix. So let's talk about some things that we need to know about that go along with this. Talk about some things that go along with this. Recall that the eigenvalues are the solutions to a polynomial equation. So recall that the eigenvalues are solutions to a polynomial equation. Polynomial equations, an nth degree polynomial equation will have n complex zeros and those counting multiplicities. So we really need to look at more cases, and we need to look at when we're going to have these linearly independent eigenvectors. So I started reversing too much in my mind, and so my sentences got a little bit jumbled. Let's get to what I wanted to say. Here's a thing that we know. I haven't shown you this. You're just taking my word for it, so proof by authority. Distinct eigenvalues correspond to linearly independent eigenvectors. So if we have a matrix, an n by n matrix, and we find that it has n distinct eigenvalues, then we'll know we'll have a diagonalizable matrix because the eigenvectors will be linearly independent. So distinct eigenvalues correspond to linearly independent eigenvectors. So this raises the question, well, what happens if we don't have distinct eigenvalues? What if we have, say, a 3x3 matrix and it has two eigenvalues because the polynomial equation had a squared term in it, lambda minus 3 squared times lambda plus 1. So it has three zeros, -1, but +3 shows up twice. So repeated eigenvalues could correspond to one or more linearly independent eigenvectors. So it could be that if we have an eigenvector with multiplicity of 2, that we get a one-dimensional or a two-dimensional eigenspace. So let's take a look at an example. Let's also note that I closed the window from which I was going to get my example. Because I was like looking at my other screen, I'm like, oh yeah, I'll use that one. And then I close the window. You know, if you had a professional teacher, you know, things like this wouldn't happen, but y'all have me, so there it is. Let's look at an example. And I'm going to, we're going to be given the eigenvalues. So let's look at an example. So A is going to be the matrix 2, -4, 3, 4, -6, 3, 3, -3, 1. The eigenvalues of A are, let's say, lambda equals 1 and -2. A is a 3x3 matrix, but only has two distinct eigenvalues. So A might be diagonalizable, it might not be diagonalizable. So that's what we want to notice here. A is 3x3. But only has two distinct eigenvalues. So we're guaranteed two linearly independent eigenvectors, but there might be three. What we do is the same thing that we did when we didn't know anything about diagonalization. We go and find the eigenvectors corresponding to each of the eigenvalues. So I look at A minus lambda I for each of the lambdas and solve the homogeneous equation. So for lambda equals 1, so we're going to solve A minus lambda I times x equals 0 for each lambda. So for lambda equals 1, I'm going to subtract 1 from the main diagonal. That's what A minus lambda I does. Subtract 1 from the main diagonal. So I'll have a 1, -4, 3. I'll have 4, -7, 3, and then 3, -3, 0. I'm going to find the reduced echelon form, see what vectors we get out of this. So let's see, math alpha B. I got 1, 4, 3, -4, -7, -3, 3, 3, 0. And here we have a one-dimensional eigenspace. I got x1 and x2 are both going to be in terms of x3. So I got 1, 0, 1, 0, 0, 0, 1, 0, negative 1, 1, 0. So x1 is going to be x equal to x3. x2 will be equal to -1 times x3, and x3 is free. There's a one-dimensional eigenspace. So the eigenvector corresponding to lambda equals 1 we'll go with 1, negative 1, 1. So there's the there's an eigenvector corresponding to eigenvalue lambda equals 1. We got to do the same thing for lambda equals 2. I've got to subtract 2 from the main diagonal. Subtract a negative 2 from the main diagonal and see what we get. So split pages and I can't remember the whole matrix. So now I'm going to solve the equation, the homogeneous equation for lambda equals negative 2. So 2 plus 2 is 4, negative 4, 3. And then I'll have 4, negative 6 plus 2 is negative 4, 3. And then we'll have 3, negative 3, 1 plus 2 is 3. I'm just writing down a minus lambda I for lambda equals negative 2. And then I'll find the reducer echelon form. So I got 4, 4, 3, negative 4, negative 4, negative 3, 3, 3, 3. I didn't hit. So, oops, close, oops, second close. 4, 4, 3, negative 4, negative 4, negative 3, 3, 3, 3. Now do I have a valid dimension? All right, don't do this without your contacts on. So I end up with, looks like we have, once again, one free variable. So I got my first column is 1, 0, 0. Then I've got 1, 0, 0 again, and then 0, 1, 0. So it looks like in this case, x2 is my free variable. x1 is equal to negative x2. x2 is free. And x3 is always equal to 0. So my other eigenvector is going to be negative 1, 1, 0. So in this case, we only ended up with 2 linearly independent eigenvectors. So A is not diagonalizable. So since A only has 2 linearly independent eigenvectors, A is not diagonalizable. This is one of the things that can happen when we have when we don't have distinct eigenvalues. We only ended up with 2 linearly independent eigenvectors. So A is not diagonalizable. So by the law of mathematical opposite examples, now I have to do one where a 3 by 3 matrix has 2 distinct eigenvalues, but is diagonalizable. If A had 3 linearly independent eigenvectors, then it would be. So what that would look like is we would see our augmented matrix, our matrix A minus lambda I would have two free variables in it. So let's take a look at another example. Let's suppose that matrix B is going to be 1, -3, 3, 3, -5, 3, and 3, -3, 1. The eigenvalues of B are lambda is equal to 1 and lambda equals -2. So once again, only two distinct eigenvalues. Right now, you're taking my word for it that there isn't a third eigenvalue that I'm secretly holding in reserve. Got to fight that instinct. Like a dungeon master, attack with the first wave, and then hold a second wave of orcs, so that when the party thinks they're about to win, attack them with more orcs. And I go, oh no, there's more. So I don't hold anything in reserve when I'm doing math problems. That's called being unfair. That's cheating on my part. So we have to do the same thing. We have to solve. We still don't know what's going to happen, although the law of mathematical examples has told us that this one is going to be diagonalizable, unless I wrote something wrong, which is totally possible. But we're still going to solve b minus lambda I times x equals 0 for each lambda. Start with lambda is equal to 1. I'm going to subtract 1 from the main diagonal, so I'll have 0, -3, 3, 3, -6, 3, and then 3, -3, 0. We'll find the reduced to echelon form of this matrix, and it looks like that -2 is going to have to be our two free variable one. So let's find out. So we got 0, 3, 3, -3, -6, -3, 3, 3, 0. Yep, this is only a oops, I didn't show you what I was typing. This is only going to be a one-dimensional eigenspace. So I got 1, 0, 0, 0, 1, 0. And -1, 1, 0. So we've got x1 is equal to x3, x2 is -x3, and x3 is free. So our vector, our eigenvector corresponding to lambda equals 1, or I should say an eigenvector, 1, -1, 1. So it's this -2 that's going to have to be, this -2 that's going to have a two-dimensional eigenspace. So let's find out. So for lambda is equal to -2, so I'm going to add 2 down the main diagonal. So 1 plus 2 is 3, -3, 3. Then I'll have 3, -5 plus 2 is -3, 3. And then I'll have 3, -3, 3. And now we can see we're going to have a two-dimensional eigenspace. This one I don't even need my machine for, because that first row is just going to take out the second 2 rows. And here are our two free variables. x1 is going to be -x2 minus x3. x2 is free, and x3 is also free. So I've got two vectors here. My parametric vector form solution, in parametric vector form, I'm going to have an x2 vector, which is going to be -1, 1, 0. And my x3 vector is going to be -1, 0, 1. So lambda equals -2 corresponds to a two-dimensional eigenspace. I can use these two linearly independent vectors. I could say v2 is -1, 1, 0, and v3 negative 1, 0, 1. So we have 3 linearly independent eigenvectors. Therefore, B is diagonalizable. Specifically, that means there's a diagonal matrix D and an invertible matrix P such that B is equal to P times D times P inverse. The diagonal matrix D will consist of the eigenvalues. Notice that lambda equals 1 corresponds to a one-dimensional eigenspace, and lambda equals negative 2 corresponded to a two-dimensional eigenspace. So my diagonal matrix D I'm just going to use the negative 2 twice. And my invertible matrix P, I have to make, since I made the first column of the diagonal matrix lambda equals 1, the first column of my invertible matrix will have to be the eigenvector corresponding to 1. Since the second and third columns of my diagonal matrix are using the eigenvalue negative 2, the second and third columns of my invertible matrix have to use the vectors corresponding to lambda equals negative 2. So I'll just put them in the order that I found them, negative 1, 1, 0, negative 1, 0, 1. Note that since lambda equals negative 2 corresponded to a two-dimensional eigenspace, how we construct the matrix P, I put the negative 2's in the second and third columns, and then I had the two eigenvectors. I could have put them in the other order. So I could have put the V3 in the second column and V2 in the third column. And that would have been just as effective. But the lambda equals 1, that has to in the first column means the first column has to be the eigenvector that corresponds to lambda equals 1. So I've got 3 different ways I can organize the diagonal matrix D. I could put 1 first, I could put 1 in the second column, I could put 1 in the third column, and that would change where I put the V1 vector. Also, for the negative 2 eigenvalue, there's 2 different ways I can deploy the V2 and V3. But I actually have an infinite number of choices, because if I want big numbers, I could say this is 10, negative 10, 10. Because I just need an eigenvector, and any multiple of our eigenvector will also be an eigenvector. So one of the things I mentioned earlier is that the eigenvalues, I reminded you that the eigenvalues are solutions to some polynomial equation. This polynomial equation had lambda equals 1 appear once and lambda equals negative 2 appear twice. So the polynomial equation equation that we were solving factored out to lambda minus 1 times lambda plus 2 squared. So it's the lambda equals negative 2 that had a multiplicity of 2. It was a 3 by 3 matrix, so we need to get a third degree polynomial equation. So we know there are going to be 3 solutions. 1 appears once and negative 2 appears twice. So what we found out in this case, the eigenvalues of B were 1, negative 2, and negative 2. Think of the multiplicity as like twins. So if you have a twin, your parents didn't have one kid, they still have two kids. So anytime students are like, oh, why do we have to list that eigenvalue twice? I'm like, oh, dude, because twins are separate people. You know what I mean? All right. I worked it out ahead of time, but I'm pretty sure that the characteristic equation for this one also had 1 appear once and -2 appear twice. Yeah, the characteristic polynomial up here was the same. Lambda minus 1 and lambda plus 2, but the -2 appears twice. But in this case, that lambda equals -2, that's the one that had a chance to have a two-dimensional eigenspace because it had a multiplicity of 2, but it didn't. So A was not diagonalizable. So it appears twice based on when we work out A minus lambda I, the determinant of A minus lambda I. So the characteristic polynomial comes from that finding that determinant. Any other questions? All right. Let us pause the video here. Drop to the end for continuity. Let's pause the video here, and then we'll come back and talk about whatever's next.